Welcome to this topic of the Demystifying IPv6 course on IPv4, IPv6 transition. This particular topic is broken up into two parts, and this is part one. So transition mechanisms have been discussed for many years regarding the migration from IPv4 to IPv6. There's a lot of different strategies that have been devised, some of them just ideas and never implemented, some of them only temporarily implemented, and then some newer strategies that are in use today. We'll cover a variety of those in this topic and the next, but it is very confusing because you'll see references to old things that were just ideas or used at one time and not used again. In this particular topic, we'll definitely cover the dual stack IP layer, the DNS infrastructure, and we'll start our discussion of IPv6 over IPv4 tunneling. But the second topic will also get into more specific examples of that, such as the most current strategy, 6RD and DS Lite, as well as compatibility addressing formats and translational mechanisms. So dual stack was defined by RFC 4213, and the idea is the nodes would actually be running two different stacks, one for IPv4 and one for IPv6, and then depending on what application and protocol they were using, they would just use one stack or the other. It's actually the most widely spread use of IPv4 to IPv6 transition because it doesn't require any tunneling or translational methods. Of course, it does require all the infrastructure, including the DNS resolvers, to support both IPv4 and IPv6 mechanisms. The idea of the dual stack architecture is to have a separate TCP and UDP and therefore IPv4 and IPv6 implementation. However, it is a little misleading because most implementations do not actually offer two completely distinct TCP IP stacks, one for IPv4 and a separate one for IPv6, but rather they have some form of a hybrid stack in which most of the code is shared between the two protocol suites. The DNS infrastructure is needed for successful coexistence because of the prevalent use of names rather than addresses to refer to network resources. Of course, this is even more true with IPv6 as we discussed in the addressing architecture, where the numbers could actually be 128 bits long. So upgrading the DNS infrastructure consists of populating DNS servers with records to support IPv6 name to address and address to name resolutions. After the addresses are obtained using DNS, the sending node must select which address to use for communication. The idea is you could send a DNS request for a specific name and actually receive back both an IPv4 and an IPv6, or possibly even many flavors of IPv6 addresses, as we talked about earlier with scoped addresses, that you might have multiple IPv6 unique addresses to select from. So a new resource record type named Quad A has been defined for IPv6 addresses in RFC 3596. So the DNS infrastructure must contain the following resource records for the successful resolution of domain names when migrating from IPv4 to IPv6. Of course, you have the original A records for IPv4 addresses and Quad A records now for IPv6 addresses. For reverse lookups, there is a new ARPA record, the ARPA domain, that has been added for IPv6 addresses as well. And as I mentioned, what if you get back multiple addresses, either a combination of IPv4 and IPv6 or multiple IPv6 addresses? So RFC 3484 was written to address that. As you can see in this slide, typically by default, IPv6 addresses in the DNS query responses are preferred over IPv4 addresses. So now that we've covered dual stack and the DNS infrastructure, we're going to take a closer look at tunneling. The idea of tunneling is to encapsulate IP version 6 packets in IP version 4 packets for transport over existing IP version 4 either intranets or even the global IP version 4 internet. Yes, it might surprise you to know that today there is a lot of IP version 6 traffic that's traversing the global IP version 4 internet, though that is considered an interim solution until everybody has global connectivity over a native IP version 6 internet. The idea with encapsulation is you set the IPv4 protocol field to 41, and that indicates that the next layer protocol is actually IPv6. And then you have your IPv6 packet inside of the IPv4. Of course, ultimately on top of IPv6 packet, you're going to have UDP or TCP and then application data. The idea of tunneling also means that the IP version 4 address is actually embedded in the IP version 6 address, so the source and destination of the tunnel endpoints can determine what is the appropriate IP version 4 addresses to populate in the IP version 4 tunnel. Tunnel endpoints are either manually or automatically configured, and we'll cover more on that in subsequent slides. So this slide provides an example of IP version 6 tunneling over IP version 4. In this slide, the big cloud in the middle is, let's consider the global IP version 4 internet. And the two hosts on each side are on native IP version 6 links. And so the routers that they're connected to locally are running natively IP version 6. And so each host just sends an IP version 6 address as it normally would, thinking that they have connectivity between each other over a pure IP version 6 internet or intranet. So the idea then is the address that host 1 and host 2 are using have an embedded IP version 4 address if it's automatically tunneled, or if it's manually tunneled, then the IP version 4 address does not necessarily have to be embedded in the address. Routers A and B actually have a link to the IP version 6 link as well as IP version 4 links, and they're considered the tunnel endpoint. So the tunnel that we're going to build here is between A and B. So router A on the IP version 4 internet side has a globally unique IP version 4 address, and router B does too. So now host 1 wants to send an IP version 6 packet to host 2. Again, the two hosts just think they're using normal IP version 6 routing, and in fact the two routers that they're directly connected to think that way too. So host 1 just sends a normal IP version 6 packet with an IP version 6 header and payload. That is eventually received by router A, and router A interprets the destination IP version 6 address. So it looks at the destination IP version 6 address and extracts what would be the tunnel endpoint associated with router B from that, either manually because it's configured that way in router A, or automatically because the tunnel endpoints, i.e. the two IP version 4 addresses of router A and B, are embedded in the IP version 6 addresses. So the table in router A says for that destination of 2, use the tunnel endpoint of 163.101.18.5 and build that as a destination IP version 4 address once you encapsulate the IP version 6 packet in an IP version 4 packet. So router A encapsulates the IP version 6 within the IP version 4 packet. So now we have a packet where you have the original IP version 6 header and payload encapsulated inside of an IP version 4 packet, and notice the source and destination IP version 4 addresses are the tunnel endpoints of router A and B respectively. Of course, the packet sent from router A to router B follows normal IP version 4 routing through the IP version 4 internet in this example. And so again, there's a lot of IP version 6 traffic traversing the global IPv4 internet using this mechanism. Router B receives the packet and then strips off the IP version 4 header. the original IP version 6 packet and payload are forwarded on to the IPv6 links that device 2 is connected to. And then it follows normal IP version 6 routing to get to device 2. So this slide just gives you another example of the tunneling format. So you start out with the original IPv6 header, possibly any extension headers, and then upper layer protocol that is transmitted. And then ultimately it gets encapsulated with an IP version 4 header where the protocol then is set to 41, which indicates that the next protocol header is an IPv6 header instead of, say, TCP or UDP. As you can imagine, since we're just adding another 20 bytes on with an IP version 4 header, for largest packet size, you need to watch out for MTU or maximum transfer unit issues then. So regarding the path maximum transfer unit, one might assume that the IP version 6 packets will not exceed the typical MTU of IP version 4, especially since IP version 6 has a default MTU of 1280 and most IP packets are carried over Ethernet links which have an MTU of up to 1500. However, since path MTU information is not stored for the tunnels, you have to make some accommodation for the fact that the packet could end up larger than an MTU of any particular link. As per RFC 4213, if the path MTU side is too large for some intermediate IP subnet, IP version 4 fragment will ensue. While this is undesirable, it's not disastrous. So when encapsulating an IP version 6 packet inside of IP version 4, the do not fragment bit should not be set in the encapsulating IP version 4 header. So as I mentioned earlier, there are two types of tunnels. There's configured tunnels and automatic tunnels. Under configured tunnels, the IPv4 address of the tunnel endpoints are not derived from embedded IP version 4 addresses in IP version 6 addresses, rather they are configured manually. The following are types of manual tunneling technologies: manual configured tunnels or generic routing encapsulated IP version 4 tunnels. Automatic tunnels do not require manual configuration. The tunnel endpoints are automatically determined by looking at the source and destination IPv6 addresses having embedded IP version 4 addresses. Embedded IP version 4 addresses and IP version 6 addresses are often referred to as compatibility addresses. The following are types of automatic tunneling technologies. There was a previous but obsolete mechanism called 6/4, which assumed that the IP version 4 network that we were tunneling across supported multicast. And as we know, the global internet doesn't, and or a lot of intranets don't either. So that particular technique is obsolete. Isotype we'll cover later, as well as 6/4, 6RD, and Torito are other examples of automatic tunneling technologies. Those will all be covered in the part 2 of this topic on IP version 4, IP version 6 transition strategies. The following slides are going to cover tunneling from a more generic standpoint. So I mentioned on the previous slide the idea of compatibility addresses, and those are those addresses where an IP version 4 is in some way embedded into an IP version 6 address. When we look at each of the protocols such as 6/4 and Isotype and such later on part 2 of this, then you'll see more about just what that means. But notice that the 6/4 address has a 2002 prefix, and then the IP version 4 address is actually the next 32 bits. So 16 plus 32 is 48. So the most significant 48 bits for 6/4 is a 2002 prefix followed by the 32 bits of the IP version 4 address, and then followed by the subnet and eventually the interface ID of the end host. And so you can determine via the www.xxyyyzz what the source and destination of the IP version 4 tunnel endpoints are, as was discussed on the tunneling example a couple slides ago. And you see similar mechanisms for the other protocols that use compatibility addresses, such as Isotype, intrasite automatically tunneling address protocol, and Torito, which is another mechanism for tunneling, but tunneling in the existence of NATs, where we need to run IP version 6 over UDP IP. instead of encapsulated directly in IPv4. So as I mentioned on the previous slide with Torido, there is a concept of NAT, network address translation, that we need to take into effect because NAT is very widespread with IPv4 today, and in fact it's the only reason IPv4 has lasted this long. So I mentioned earlier you have two types of tunnels, configured and automatic, but then there's also configured and automatic in the presence or absence of a NAT. So there basically translates to four different categories of tunnels. A few comments regarding tunnels to make here. Configured tunnels only operate point to point, whereas automatic tunnels can be point to multipoint. A couple examples of automatic tunnels in the absence of NAT is 6 to 4 and more currently 6RD. Again, we'll discuss those later on. Torido is an example of a solution for an automatic tunnel over IPv4 across a NAT environment. RFC 2893 was the main standard that defined transition mechanisms for IPv6 hosts and routers that has subsequently been obsoleted by RFC 4213. One of the things obsoleted was this concept of automatic tunneling. RFC 2893 had a concept of that, but a more general mechanism was written, RFC 3056, which defined the 6 to 4 mechanism. Although RFC 5569, which is 6RD or IPv6 rapid deployment, is now preferred over 6 to 4, and we'll discuss more about that in the second part of this topic. So now RFC 4213 only defines dual IP layer and configured tunnels, so it has no reference to automatic tunnels anymore. It also defines node types and tunnel types. RFC 4213 defines the following types of tunnel configurations: router to router, host to router, router to host, and host to host. And depending on what you're trying to accomplish, if it's router to router, it generally means that you have one version of IP on the endpoints and another version in between. So as discussed a few slides ago, we had IPv6 on both ends and IPv4 in between. So we needed a router-router tunnel to get our IPv6 traffic over the IPv4. There's also circumstances where you might have IPv4 on the end and IPv6 in the middle. And so we'll address that in the second part of this as well. Host to router and router to host means that the host is connected to one type of protocol but trying to run another over it. So instead of the host trying to send IPv6 packets over a directly connected IPv6 link, what if a host needs to send IPv6 packets but it's only connected directly to an IPv4 link? So host to router and router to host address that. With host to host, it's similar to host to router, but now both hosts are actually and generally on the same subnet as far as the IPv6 protocol is concerned, but they're both connected directly to IPv4 with no other tunneling required in between. One interesting note about tunnels is all the tunneling mechanisms, whether they're configured or automatic, there is no tunnel setup, maintenance, or termination. So the tunnels don't need to be signaled, such as this case with MPLS. And none of the tunneling techniques that we're going to describe provide security. So if you want to secure your traffic over the tunnels, then you need an additional layer of IPsec, for instance, for that purpose. So these tunnels are just connections, so to speak, but they're not signaled. So router to router tunneling, like I mentioned and we saw a few slides ago, is when you're in this example, your two IPv6 nodes are connected to IPv6 and they need to connect over an IPv4 infrastructure, so the two routers in between need to establish a tunnel for those packets. Some of the examples of router to router tunneling include, as I mentioned earlier, automatic tunnels such as 6 to 4 and 6RD when you're trying to tunnel IPv6 packets across an IPv4 internet, or sort of the reverse thing when you're trying to send IPv4 packets across the service provider's IPv6 infrastructure, then we might use DS Lite. Host to router tunneling. In this example, let's say node A wants to send an IPv6 packet but is only directly connected to an IPv4 infrastructure. So host A is actually an endpoint for the tunnel. Some of the examples of host to router and router to host tunneling: an IPv6 host that needs to tunnel across an organization's IPv4 infrastructure to reach the IPv6 internet. An example of host-based tunnels is Isotype, which we'll describe more in the second topic. Another example of a host-based tunnel is Toredo if you're running in the presence of a NAT. Host-to-host tunneling is when, let's say, you have two IPv6 hosts that are both connected to an IPv6 infrastructure. They can reach each other directly over the IPv4 infrastructure, so no routers are required, but they need to establish the tunnel to get their IPv6 traffic over an IPv4 tunnel. And again, just like with the host-to-router function, the Isotype is the most common example of host-to-host tunneling. Implementing IPv4 tunneling for IPv6 then. So there are a variety of overlay tunnels, protocol-based tunnels, IPv6 over IPv4, possibly even IPv4 over IPv6. So as we talked about earlier, there's a couple different types of manually configured tunnels and various flavors of automatically configured tunnels, whether it's host to host, host to router, router to router, in the presence of NAT or not. So with overlay tunnels, IPv6 packets are encapsulated in IPv4 packets across an IPv4 infrastructure. It allows communication between isolated IPv6 networks without upgrading the IPv4 infrastructure between them. It can be configured between border routers or between a border router and a host. Both tunnel endpoints must support both IPv4 and IPv6 protocol stacks. In other words, they need to be dual stacked. They also have maximum transfer unit issues to keep in mind, as we discussed earlier. And a key thing here is tunneling in general should only be considered as a transition technique toward a network that supports either both protocol stacks or ultimately just the IPv6 protocol stack. And when we say a network, we mean everything: the hosts, the routers, and everything in between. So this slide talks about different types of tunnelings and suggested usage. So we start off with manually configured tunnels. They're the simplest point-to-point tunnels and can be used within a site and between sites. They can carry IPv6 packets only, and that's the key differentiator between that and a GRE tunnel, because GRE tunnels can carry a variety of different types of traffic. Automatic tunnels, so you have what was originally referred to as a compatible IPv6 tunnel, where you had all zeros ending in the 32 bits of the IPv4 address. That's no longer recommended. Obviously, there is no routable portion from an IPv6 perspective. There's Isotype tunnels, which, just like all automatic tunnels, are point-to-multipoint tunnels, are used to connect systems, in other words, hosts. So they're host-to-host, host-to-router type of tunnels within a site, hence the intra-site designation of the address. And what this allows, Isotype also allows sites to use any IPv6 unicast prefix. We'll cover that more later. The original form of tunneling isolated IPv6 sites across an IPv4 network was the automatic 6-to-4 tunnel. And as I mentioned earlier, sites use the address prefix of 2002::. But automatic 6-to-4 tunnels are being replaced by automatic 6RD tunnels, and so that allows the sites to use any IPv6 unicast address as opposed to the 2002 prefix. Manually configured tunnels are the equivalent to a permanent link between two IPv6 domains over an IPv4 backbone. Manually configured tunnels are inherently point-to-point between border routers or even between a border router and a host. So therefore, an IPv6 address is manually configured on a tunnel interface and in the routing tables, and manually configured IPv4 addresses are assigned to the tunnel source and destination, but manually. In other words, not extracted from the accompanying IPv6 packets addresses. Just like any tunneling technique, the host or router at each end must be dual stack. Manual GRE or generic routing encapsulated IP version tunnels provide a similar point-to-point service and are manually configured, but they are not tied to a specific type of protocol for transport. In other words, instead of just transporting IPv6 traffic, you could also transport other protocols such as ISO protocols as well. So you have an encapsulation of the layer 2 header of the link that you're sending on, the tunnel IPv4 header followed by a GRE header, and in the GRE header it would indicate the protocol that tunnel IPv4 is carrying. And in the case of IPv6, it would be the original IPv6 packet encapsulated following the GRE header. So look forward to part 2 of this presentation, which will discuss in more detailing specific tunneling techniques such as 6RD, DS Lite, as well as translation mechanisms for IPv6 transition. Otherwise, thank you for taking the time for viewing this topic of the Demystifying IPv6 course on Transition Mechanisms Part 1.